everyone. Today we're going to talk about momentum and impulse. All objects with mass have inertia, which is proportional to how massive the material is. The greater the mass of an object, the greater is its inertia. Inertia is the tendency of an object to remain at rest or moving at a constant velocity unless a net force not equal to zero acts on it. This is Newton's first law of motion, and according to Newton's second law of motion, behavior of the mass, the greater must be the force acting on an object to cause a certain amount of acceleration. So think of inertia as like friction, except that friction is the resistance to motion when two surfaces are rubbing against each other. Inertia exists in the material itself, in empty space, and it's the resistance to changes in motion. It's resistance to an acceleration due to a force. Inertia resists these changes. When an object is moving, it has momentum, which is proportional to its inertia and mass moving at a certain velocity. So if you have a massive object moving with a velocity, that motion is called momentum. And momentum is represented by the letter P with an arrow on the top, meaning it has direction because it's a vector. And the part of momentum that is a vector is its velocity, not its mass. To cause a change in momentum, there must be the presence of a net force acting on the object that is not equal to zero. Force is a vector, thus it has the triangle, the arrow on top, and then acceleration is also a vector, which is why it has an arrow on the top. Force equals mass times change in velocity over change in time. If you bring the change in time and multiply with F, you get F dt equals mdv. Force times the time into which the force acts on the object is equal to the change in momentum due to a change in the object's velocity. This is the equation for impulse. Isaac Newton, while he was writing the book called Principia, investigating mechanics and kinematics and forces, he came up with the equation F equals ma derived from the change in momentum. So I strongly recommend you read Principia because everything we know in physics, in mechanics and kinematics, angular momentum, torque, all of that stuff was discovered by Isaac Newton, and he came up with the equation F equals ma derived from the equation of impulse F dt equals mdv. When a ball is traveling in air and it hits a wall, during a collision it undergoes an impulse. The ball deforms during collision and then reattains its original shape bouncing off the wall, right? The ball hits the wall, it deforms, it gets squished, and then when it stretches back, it bounces off the wall. The velocity of bounce will not be the same as before collision since some of the energy is lost during collision converted to sound and heat. And this right here is the graph of the force between the ball and the wall. It increases, it reaches a peak, and then it decreases and it goes back to zero. And that's when it goes back to zero is when the ball rebounds from the wall. And the time during collision is from the beginning of the peak to the end of the peak. So pretty much the beginning of this graph and the end of this graph. Force times time equals impulse. The area under the curve of a force versus time graph is impulse. Area under the curve is mdv, with dv being v final minus v initial. So you can actually calculate the velocity of the bounce of the ball if you know the area under the curve then describing the force during collision over a time interval during collision. Yes, collisions are not instantaneous. They have a time during the collision. So they last, even if they last fractions of a second, most of the times, yes. They act, the force acts as during that time leading to the change in motion. When objects collide with each other, they lose energy and momentum. That's a fact. To facilitate calculations, physicists have described two types of collision. Elastic collisions when energy and momentum is conserved, which is also known as an ideal case. There's no such thing as conservation of momentum. Momentum is always lost. Now, if you think of a closed system, the universe in itself, maybe momentum and energy is conserved in the universe itself. But there's no closed system within the universe because there's always going to be losses of momentum and energy during collisions because energy is given off as heat and sound, and momentum is lost because if you have a Newton's cradle and you pull one ball, when they bounce, every time they come back and they go up and they come back, they seem like they're losing momentum. So those collisions are not elastic. Inelastic collisions when only momentum is conserved. Even that is not true. All collisions in the universe are they lose momentum too. So all collisions are inelastic, but even more so in the fact that they lose momentum. Both cases are actually ideal since momentum is always lost in collisions, and all collisions in the real world are inelastic since energy is also lost. Example of elastic collision. Red ball of mass m moving at a velocity v, and then it collides with another ball of mass n. They collide, and then after collision, the first ball stops and the second mass moves at velocity v, the same velocity the first ball was moving. Total momentum must be conserved, so the velocity of the second ball after the collision is exact same velocity as the first ball, and because both balls have the same mass, the kinetic energy is conserved, which is never true. Example of an elastic collision, red ball of mass m moving at velocity v and then collides with another ball of mass m. They collide with each other and then they stick to the second and both move at velocity v. But this v is different than the original v, right? Total momentum must be conserved, so mv initial is equal to 2mv final. Now, two masses moving, and because you have two masses moving together, there's more mass, so Vf will be less than the initial velocity Vi of the first ball before collision in order to conserve momentum. So in order to conserve momentum, the velocity after collision has to be less than the velocity before collision of that one ball because there's more mass moving, so they have to move slower. And because momentum is mass times velocity, if you have more mass moving, the velocity should be less to counteract the fact that there's more things moving. Energy is not conserved, however, initial kinetic energy is equal to final kinetic energy, is not equal to final kinetic energy. So that means that the initial kinetic energy will be will be more than the final kinetic energy. Other inelastic collisions, heavy mass hitting lighter mass. Um, So a heavier mass comes in, hits the lighter mass. The heavy mass continues moving to the right at a slower pace, and the lighter mass just shoots forward at a really fast pace. Momentum is conserved, but energy is not lost. Other inelastic collisions, lighter mass hitting heavier mass. They collide, the lighter mass bounces off back because it's lighter, and then heavier mass moves to the right just slowly, and collision is inelastic and momentum is conserved but energy is lost. So this was a short introduction to momentum, impulse, and collisions. Thanks for watching.